Okay, we're talking 2.2 today, inductive and deductive reasoning. Okay, basically coming up with patterns to come up with a solution. First one here. We have to write a conjecture about the pattern, then use your conjecture to draw the 10th object in the pattern. Okay, so first find the pattern. Well, what I see is a bunch of triangles, and I see this dot here. And that dot moves through the triangle. Here it's bottom right, bottom left. This is top, and then it goes right, left, top, and then right. Okay, so what I see is that it's kind of going counterclockwise. Counterclockwise. Okay, and it's going one direction, right? In one spot each time. So in the 8th, it's going to be in the left. In the 9th, it's going to be at the top. The 10th place, it's going to be in the bottom right. Okay, so if I were to draw it, I'd draw my triangle and then my circle right there. Okay, second one, B. Okay, it's same thing. It's going counterclockwise, right? So I'm going to say counterclockwise. But it's switching between a curve to a straight line. So curve, then straight. Okay, and the curve is kind of changing as well. Notice how this curve is going up to the right, this one's going down to the left, this one's going up to the right, right? So the other one was kind of over, this one's going out. Okay, so it's going to keep changing. So what is this? This is the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th. We need the 8th is going to be a straight line going out. The 9th is going to be kind of a curved line that looks like the first one. But the 10th is just going to be a straight line in that bottom right-hand quadrant. Okay, I'm going to skip C because we have a lot to get through today, and C is kind of a bad example of patterns. Explanation 2. If an item, okay, so here we're looking at this Venn diagram on the right. Okay, and what we're doing is just seeing if the statement is true or if the statement is false, just based on that Venn diagram. Letter A. If an item has property B, okay, so find property B. It's over here, right? It's this right here. Then it has property A. Is that true or false? It's true. Why? Because property B is contained by property A. So all property B is in A. Letter B, if an item has property A, then it has property B. Is that true or false? That's false. Why? Find any spot in property A that's not in property B. For example, here's property A, that's not in property B, right? So some property A is not in B. Scrolling down here. Okay, same thing. If an item has property A, then it has property C. Is that true or false? That's false, right? False. Why? Because look at all this property over here. That's not in A. Okay? D, we're on letter D. Some items that have property A do not have property B. Is that true? For sure. That's true? Yeah. You can have property here That's not property B, or here, or here. Those are properties that are not in B, but still in A. If an item has property C, then it does not have property B. Is that true or false? True, right? All of property C, right here. Nothing in that contains property B. So that's true. F, some items have both properties A and C. Yeah, that's true, right? Right here. Some of them, not all, but some. So that is true. And some items have properties B and C. Is that true or false? That would be false. Right? Because all of C, or there's no B in C, so that is false. I'm not going to do the third exploration. Number 4, how can you use reasoning to solve problems? Well, you can come up with patterns, or find patterns that lead to a result. Okay, you can find some sort of pattern that gives you a good guess or approximate answer. Number 5 says, give an example of how you used reasoning to solve a real-life problem. Give an example of how you used reasoning to solve a real-life problem. I'm going to use a math example because that's who I am. That's what I like to do. Back in high school, if I were to take a math test, if I studied, if I study for 45 minutes the night before a test, I got at least a B. Okay, so what do you think I did before every test? I studied for 45 minutes prior, or the night before that test. Okay, that's my reasoning. My reasoning, I studied 45 minutes. Why? Because I'd get at least a B on my test. In your own words, again, if your words don't match mine, that's fine. I'm going to write what kind of a book says, what I kind of interpret it. First one, conjecture. A conjecture is an unproven statement that is based on observations. Okay. An example of a conjecture would be that I was going to at least get a B on that test. Is that necessarily proven? No, because I could still do poorly on the test or mix up my problems and get a few wrong, right? So it's not a proven statement that I get a B on it every single time I study for 45 minutes, but I had a pretty good guess because most of the time when I studied for 45 minutes, I got at least a B. Okay? But I could still fail that test. So a conjecture is an unproven statement that is based on observations, not proven. Okay? Inductive reasoning. Inductive reasoning is finding a pattern in specific cases and then writing a conjecture. Okay, so inductive reasoning is finding a pattern and then coming up with your observation. That's inductive reasoning. Okay, I'm going to skip ahead and go to deductive reasoning down here. Deductive reasoning is a little different. Where does the book say? Deductive reasoning uses facts. Uses facts or proof. Okay? Deductive reasoning, you have to have proof or facts or properties or laws of logic. Okay? Deductive reasoning is, it's there. It's a fact. Okay? And then I'm going to go back to counterexample. Counterexample is just one case. All you have to do is find one case that proves the conjecture false. Okay? So there's one case or one instance that proves the conjecture false. That's a counterexample. Okay? I'm going to pause the video. I'll be back in a moment to finish out the rest of the video. Alright, after our definitions, we have a few readings that might be okay. Inductive reasoning, we kind of went through that. Counterexample, talked about it. Let me move this out of the way. Down here, this is very important to look at. Law of detachment. If the hypothesis of a conditional statement is true, then the conclusion is also true. Okay, just know that. We're going to be looking at an example of law of detachment here in a little bit. The law of syllogism. The law of syllogism. Okay, I like to call it the chain rule. Why? Notice it says if P then Q. If P then Q. Then it says if hypothesis Q then R. Okay? Notice if P then Q. If Q then R. That Q is the same thing. Okay? If P then Q. If Q then R. Therefore, we can finally say if P then R. Okay? Again, we're going to get into an example of this here in a second. Here's a couple extra practice problems. Describe the pattern, then write the next two numbers. Okay, so we have 20, 19, 17, 14, 10. I always like to look at the difference. Okay, so there's minus 1. Here's minus 2. From 17 to 14, it's minus 3. From 14 to 10, it's minus 4. Okay, so the difference is getting bigger, right? The difference from each number. So if I were to describe this pattern, I'd say the difference is going up by 1 each time. Okay, something like that. Again, might not be the best wording, but if I can understand what you're trying to say, perfect. Okay, write the next two numbers. Well, 14 to 10 is minus 4. We're going to go minus 5, so the next one will be 5. It will be minus 6. It should be negative 1. This next one, we have 2, negative 3, so I'd say, well, that's kind of plus 2 to 3, that's plus 1, right? And it's becoming a negative. Okay, and then it's, well, plus 2 from 2 to 5, or from 3 to 5, that's plus 2, but it goes from negative to a positive. Our pattern kind of gets screwed up because, look, it's plus 2 again. So that can't be our pattern. We have to look at something else. Find something that all these numbers have in common. They're all what? Prime numbers, right? And they're switching from odd, or not odd. They're switching from negative to positive. Okay, so the next two numbers. What's the next number? What's the next prime number after 11? It's 13, right? And 11 was positive, so our next number has to be negative. What's the next prime number after 13? 14, no. 15, no. 16, no. 17, right? It's a positive. There's my next two numbers. Five and six, we are making a conjecture. We're making a statement. Okay, we're coming up with some patterns, coming up with any type of reasoning to show that the sum, or to show what the sum of two negative integers is. Find any two negative numbers, any two, doesn't matter. I'm going to say negative 5, and the sum, what does sum mean? It means plus. So you have negative 5 plus a negative 8, doesn't matter. What does that equal? It equals negative 13. Maybe another example, negative 92 plus negative 4. That equals negative 96, right? So, what can I say? The sum of two negative numbers will always be what? Negative. This next one. The product. What does product mean? Product means multiply. Of three consecutive non-zero integers. So any three non-zero integers. Consecutive, so 1 times 2 times 3. What does that equal? It equals 6. What's another one? Let's do 4 times 5 times 6. That equals 120. Okay? So the product of three consecutive non-zero integers is always what? Even. Based off my couple examples here, the product of three consecutive non-zero integers will always be even. Okay, next one. Find a counterexample. All I'm looking for is one example to prove that this is false. If n is a rational number, what's a rational number? A rational number is a fraction. So let's find a fraction, any fraction. 7 over 2. Okay, then n squared is always less than n. What's 7 over 2 squared? We have 49 over 4. Is that less than 7 over 2? No. Right, so here's my counterexample right there. Done. Done. 8, line K intersects plane P. So if I have a line right there, intersects plane P at point Q. Here's my plane P. Point Q is right there. Plane P is perpendicular to line K. Is that perpendicular? No. So there's a counterexample. In exercises 9 and 10, use the locked attachment to determine what you can conclude from the given information. Okay, so if a triangle has equal side lengths, then each interior angle measure is 60 degrees. Is that true? Yes, right? An equilateral triangle is also equiangular. So triangle ABC has equal side lengths. Here we go. ABC has equal side lengths. So what does that mean? Each interior angle is 60 degrees. Okay, that's the law of detachment. Next one. If a quadrilateral is a rhombus, then it has two pairs of opposite sides that are parallel. Quadrilateral PQRS has two pairs of opposite sides that are parallel, therefore what? I could have said quadrilateral PQRS is a rhombus, but I just said it is a rhombus, okay? Okay, 11 and 12, we're talking the law of syllogism. And we're writing a new conditional statement. What's a conditional statement? Our new conditional statement is if P, then Q. Or if, then. That's a conditional statement. 11 says, if it does not rain. Sorry, let me scroll down. That's the bottom. Okay. If it does not rain, then I will walk to school. So I have P, I have Q. If I walk to school, okay, so that's the same Q, right? Then I will wear my walking shoes. That's R. So if it does not rain, then I will walk to school. If I walk to school, then I will wear my walking shoes. So my new conditional statement is, if it does not rain, so if P, then R, then I will wear my walking shoes. Okay, that's my new conditional statement. Number 12. Number 12 is a little different. Number 12 is a little different. Remember, we have to have if P, then Q. If Q, then R. So we have if x is greater than 1. That's P. Then 3x is greater than 3. Q. If 3x is greater than 3, maybe it's not different, then 3x squared is greater than 9. R. So this isn't different. This is the same thing. Our new conditional statement is if x is greater than 1, then 3x squared is greater than 9. So if P, then R. That is the law of syllogism, or chain rule.